Welcome today to the wood frame building over Podium Slab webinar. We've got a picture here showing kind of similar to what we're talking about. The idea here is that we'll be building a multiple story building of lightweight construction, so wood construction, and we get to utilize the lower level as a retail or garage or some way to utilize that structure and to support the lighter structure above it. So I did a bunch of these types of buildings on the East Coast in the New York area, but I know that this is kind of a trending, and I see this in California now here a lot. So it's a useful webinar for you, hopefully, to see this different type of construction and how we do it in RISAFloor. So starting out here, I'm going to jump to RISAFloor directly here. I'm going to click on that. So the way I'm going to start this building is actually by using the DXF input. There's a couple different ways you can import directly into from a DXF. So the lower structure here, if we take a look at my AutoCAD drawing here, I have just drawn out the slab edge, the columns, the walls. I put some parking in just to get a feeling for how this whole layout would fit. And I'm going to import this into RISAFloor. So starting out, I'm going to start a new floor plan. Then this is going to be my concrete floor slab level. So I have two choices. I have a concrete floor slab or a beam supported floor. The very bottom of my structure is going to be concrete floor slab. And the elevation here I'm going to say is going to be 15 feet. Beyond that, I'll leave everything else. I'm just going to say okay. And I start off from scratch here with a brand new floor level. In here, we've got some options here to either import a drawing grid, do a drawing grid, import a DXF, and that's what I'm going to be doing. You could start from scratch with a project grid, but what I'm going to do is here what's called an import DXF as a drawing grid. So what I like to call this as an underlay. I'm not actually importing that AutoCAD drawing. What I'm doing is just importing the outline of it in order so I can sketch on top of it. I'm going to let it go to 0, 0 origin. I'll leave all the scale factors as 1, and as my drawing is in inches, so that's fine. All I need to do is just browse for the file. So it's sitting in my RISA folder. I just find that lower slab building and say OK. And I'm going to import all the layers of that building and say done. And you'll see it's just a gray outline. This isn't a model, so you can see I can't click on anything, like there's not actual pieces of the columns or anything like that. It's just a good background image for me. So one of the things I want to start with is drawing my columns, and you can see they're kind of close to this parking, so it's a little hard to click. So instead of just bringing the entire drawing over, what I'm going to do is I'm actually going to bring in certain layers of that. So instead of doing that, I'm going to go back to a lower slab building. Instead of bringing all of them, I'm going to say select layers from a list. So I'm going to pick all the layers I have in the structure except parking. So that makes it easier for me to see. Now you can see that it's now the parking is missing. So to start by drawing just columns, I have little columns here located here. I'm going to click on the columns, and in RISAFloor, this is actually what we call RISAFloor ES. It's the elevated slab portion of RISAFloor. And this it was a little different than it's assuming I'm doing a concrete column, so it doesn't ask me what type of material to use. I can use explicit shapes if I want. A lot of times when I worked in concrete buildings, we had a explicit shape. We knew what the architect would allow us to do, so the program sizing it up wouldn't be helpful. But I'm going to let the program actually size it for me. I'm going to choose a 4,000 normal weight. I could change the design rules here, but what I'm going to do is just let the program go with its defaults for now. I'm going to call it lateral, and I'm going to say apply. Now, all I need to do is just highlight across this box, this area here, and it's clicking to the DXF underlay. So it's easy for me to create these columns. And in my AutoCAD drawing, all I did back on the AutoCAD side was I created blocks for my columns. So I can just kind of drag across just like this, or anything to be able to click to those members, those little block locations for my columns. I'm going to right click and drop that. And the next piece I'm going to do is draw up in some of these walls. So this is my elevator area. I'm going to use masonry actually just to show some different types of materials that we can do. So I'll call this a lateral masonry wall. I can say apply and just sketch directly. It gives me those points to click to. And then the next piece here, I'm going to say that these outer edges of these walls are going to be actually concrete. So I'll go ahead and click on concrete and lateral as well. I can choose this to be 4,000 normal weight as well. And then what I'll do is I'll just click around the edges. So you can do a giant wall across the back end. What happens there is that you're going to get reinforcement similar for the entire wall. Maybe there's just portions of the wall that might not be, maybe there's a higher stress or whatever. So a lot of times you break this wall up. It's not typical that you build a giant wall. So what I'm doing is just kind of grab a point and grab it across the entire thing. You'd want to set that up in your DXF if you wanted to. You just draw in separate lines, or you can just find along the way. So I'll be able to click to different points along my wall back here. Same thing over here. I have a point right here. I'm going to click along this whole wall to find my points. So I'll go across and then I'll go back up here. So I have all of my lower level of my structure in place. So all my supports are there. We can look at it in 3 dimensions just to kind of see how it looks right now. So just columns, walls. You'll see those were the masonry walls, my concrete walls. If we go back to plan here, you can see I'm going to actually go back to my plan view. And the last piece for me is my slab edge. So in order to draw that slab edge, it's a little different on this concrete level. You can do kind of anything you want. I actually have my slab edge drawn in. We're using a semi-rigid diaphragm. This is going to be using my slab definition semi-rigid diaphragm. It's a 12-inch thick slab and it's 2A reinforcement. So I'm going to go ahead and draw that slab semi-rigid diaphragm here in. And I just go draw. I can just trace what I have for DXF all the way around the structure. So we've got that in place here, and you'll see that green outline that shows me that slab edge. I could have made any type of shape just to kind of, this happened to work nice for my podium, but if I had any other type of concrete structure where I had any edge, it doesn't have to follow your framing. It can be a cantilever of any sort, things like that. So when I have all that in place here, the next piece I'm going to do is add some openings in the structure. So you can put openings anywhere you want. I'll put some openings here, some obvious places like I'm going to do a rectangular opening there right inside of my my elevator shaft. So if I click inside of here to create this opening, and then if we do, this is a podium here. This is going to be, it's got to have some sort of opening to get down, like a ramp type of opening. I'll just place that in there. Obviously, you might want to go ahead and put other types of openings across, but just to give us an idea of how to add that opening here. So you see it's just not part of the slab anymore. Then once we have all that in place, the next piece we're going to do is add our support lines. So once we have our design done on the whole structure, what we're looking for is reinforcement in this model. So support lines are how you find that reinforcement. So I tell the program north, south, or east, west. It doesn't have to be strictly north, south, but we were looking for 2 orthogonal directions or closely orthogonal-ish area directions. So we have north, south, east, west, and then we have rebar rules that follow that. So what we'll do is we'll pick out a support line, a support to support. So you'll find I'm just clicking on either the edge of a wall, I'm grabbing the edge of a column and going across here. So I'm just drawing support lines. Now, once we finish drawing in all of these support lines, you'll see here we'll just create we're going to actually generate the design strips from these support lines. So you'll notice I'm not really being exact. I'm just trying to find quick edges. It's not really a exact science on how you click. You just sort of find a direction here, click on a support line, and keep going. So anywhere along this wall will work. I'll do the same here. So we'll bump through all the north-south lines, and we'll kind of see once we finish what this is going to look like. Common question you get is, should I draw a support line along the wall? The stresses will be pretty low along that wall, so you could if you wanted to, but you'll just notice that the design for that area will be so small that you might just want to bump the design strip out and then gauge that from there, but you could draw it along these walls. I'm going to go ahead and do the other direction real quick. So we'll go east-west in both ways, and we'll finish this up here. So clicking on that east-west direction. Of course, this is a 2-way slab. So we're trying to click it in 2 ways. That's kind of the big point, right? You have to go in both directions in order to get designed properly. And the program will then create those design strips for you. Okay, so last couple lines in place. And what's good about these openings too is you're going to notice it's going to cut around the openings. It's pretty smart about understanding that there is an opening there, that we're going to figure out how to get design around that opening. Okay. So once I have all that in place, I click on Generate Strips. And what the program does, it gets a little crazy with two ways, so we'll just change this to one direction at a time. So for example, north-south, if we're looking at here, what it did is it expanded that from the support line out to the neighboring support line that it found, and it created a design strip. So it does a real good job on some of these ones that are pretty simple. Every once in a while, you can see it looks for a neighboring strip, and it went too far. That's not a problem. It's so easy to fix. You just go over to the modify area and you have a couple different ways. You can either redraw the edges or edge align. I'm going to do edge align for a couple of these. So for example, this one here has an edge that went too far. So I'm going to take that edge and align it with this edge. Okay, I'm going to do the same thing. Take this edge and align it with that edge. I'm going to go out to this edge here and I'm going to align it with this edge. So you can kind of start to see I'm pulling these back a little bit. And some of them are you might want to play around with a different tool we have. So you can see here the redraw edges. Maybe that's easier to grab that edge. So for example, I'm going to grab this edge over here and I'm going to drag it back. So the idea is that the program gets you pretty far and pretty smart about what it's doing, and that you can quickly grab things and modify them in order to get them to where you need them to be. So it's pretty easy for you to do that. So we'll grab this one, and actually this one is the one we want over here. And you'll see. So you're blanketing the slab, trying to find the forces within that slab and the max and the mins to try to get the what you need for reinforcement. That's what we're doing with a design strip. So we'll pull this back. There we go. So I've kind of cleaned it up, and you say it just takes a couple seconds in order to get all of these sort of cleaned up in a way that they all look like we're now grabbing all the design strip areas that we need. So you can do that in both directions. I'll skip the other way. It's pretty probably actually. If you look at, there's some quick tools here for you can look at the east-south and then east-west, excuse me, and then we can just see this looks pretty clean. So we'll let this stay the way it is for now. So I'm going to go ahead and go back to north-south. Okay, so we've got all our support lines in place. Now let's just take a little look at the loading. So if I go ahead and look at my area load definitions. So this is a floor level we talked about earlier. We just created a 15 feet. It's in the floor level. There we see it's office loading. Probably this isn't an office. Maybe what we call this would be maybe retail, or maybe residential. So, but we'll call this actually retail level. So I'm going to create a new one called retail. And in that retail here, I'm going to give a post dead load. The post and the pre really just refers to some steel. So for us here, we're actually more worried we'll just call it post DL. We're not doing any steel design here. So we're just going to lump it all into the post dead loads. And I'm going to give it 10 pounds or 0.01 kips per square foot. For the live load here, if we're in retail, we're probably a little higher, so maybe 100 pounds of live load, and then we'll call that actually to be reducible. Vibration will skip. That's also a steel thing. I'm going to jump over here to the dynamic loading. And this is the number that's going to be dumped into the dynamic mass when we go over to RISA 3D to calculate the seismic mass of the structure. So I'm going to call that 0.01. So that's 0.01. So it's 10 pounds per square foot, matching what I'm using here for my dead load. So I've got that in place. Let's call this residential instead of office for my other floor levels. I will also be using roof, so you can kind of dial in what you have for the rest of the structure, but all these look pretty good to me. So what I'm going to do is go ahead back to my area load default and call that retail. So if you look at this now, the whole floor is getting a default area load of, when we look at the right here, we can see it says retail. So all the loads on the structure here level is going to be retail. We might change that here coming up in a second, but we'll leave that for now. This is our default area load. So the next piece here we're going to do is get that upper structure in our model before we do much with this lower structure. So let me turn off that. And instead of using a DXF underlay tool, I'm actually going to import the DXF. So if I go to File, Import, this is another way to bring a DXF into the structure. So I go to DXF File, and I'm going to find here my upper wood wall building revised. That actually looks like, let me show you. Well, you can see here, it looks over here. You can see I just drew out the edges of the wall in DXF. So I've got my wood walls. I've got my core wall here for my concrete. Actually, that's masonry core for my structure, for my elevator shaft. So I have all my walls drawn in DXF just because it was really easy for me to draw this in DXF. Maybe you get that from the architect. It's kind of an easy way to start a structure. So I'm going to say upper wood wall revise, say open. And all I did really was bring in walls. So I'm not going to worry too much about anything else, just the wood walls. I'm going to say that this floor elevation here is going to be at 30 feet and it's a beam supported floor. This is the upper level floor. So this one's not a concrete floor slab. This one's going to be when I start my wood structure. So I'm going to say, okay. And I jump into my upper floor. This is sitting right on top of my lower floor. So an easy way for me to see that it is doing that is actually to go to my plot options and I go over to the miscellaneous tab and I can say show the floor below the current floor. Then you can see there's an outline of the floor below. That gives me a good idea. First of all, did I land the structure properly on the structure below? That's important. But also now you can see I can kind of trace those concrete walls or masonry walls, excuse me, that I did not import through the DXF. So I can do that here in a sec. But let me turn this off for just a second here because what we want to do is worry about what came in. These are right now, the program didn't know, it's just DXF, so they're just general walls. So we're going to make sure that we tell the program what kind of walls we want to use. So we go ahead and go to the wall design rules. And we're going to go to the wood design rule here called typical and just take a look at what we have for a wood design rules. I'm going to use, instead of a 2x6 across the board, I'm going to use a 2x8. So I'm going to use the top plate's going to be two 2x8s, the sill plate will be 2x8, the studs will be 2x8, and everything else looks good. My headers should be fine. You can have the program size the studs so the spacing will be increased or decreased. I'm just going to say use 16 on center and go with that. I'm going to go over to the wood wall fasteners, which is really what we're worried about when we get to the lateral loading. And then here, I'm going to tell the program that I want my chords to be 2x8s. And that's kind of where all I need to set up so far. So going back to this floor level here, I'm going to just go single view here, change this. So I'm looking at just this floor level. I'm going to change this so all of these general walls are now going to be using wood walls. So in order to do that quickly, I can go ahead and click on the modify walls here. And instead of the draw, we go to the modify. And I'm going to say use wood. And I'm also going to make sure they're lateral and apply to all selected walls. So an important note, why am I calling everything lateral? Well, I'm going to bring the entire model over to RISA 3D. That's really all I'm doing by calling it gravity or lateral, is making a decision whether I want this entire structure over to RISA 3D. So all my wood walls I want over to RISA 3D. I'm also going to bring this core wall here as well. So I'm going to put that wall there back in as an under. So all it is showing me what's underneath it. I'm going to draw that masonry wall on top of that. So I'm going to say masonry, lateral, and go ahead and just trace that lower level. And now we see I've got the lower level in place. I'm going to turn that off one more time here. So under miscellaneous, just show another floor and I turn that off. Okay, so I've got the outline of all my walls in place. The next thing I'm going to do here is I'm actually going to just draw in a steel beam across that elevator. So I'll just call that gravity. We'll just call it A992 just to help us with our gravity, with our elevator. So it's just one little piece of steel. Just shows you can do any material type you'd want. The next thing I'm going to do is just draw some of the wood framing in. I'm going to do some repetitive framing, but for me here, I'm going to just pick a glue lamb. I'm going to tell the program here just to draw point to point. And I'm going to frame some of these larger areas in. So I'm going to close this area off across this hallway. So this would be more like apartments. I've got some apartments across the structure. I'm going to put some infill framing in the different directions, all in these different bays. And then I'm going to just draw this off here. So the program's really smart about infill framing. Sometimes in some of these little areas you can draw across and it will help you to infill a bit. So I'm going to use the infill framing next. Now, infill framing, you have some decision. You can use some wood products instead of just glue lam. You have things like I-Joists. So you have a laundry list of different I-Joists that we've had for different manufacturers. I'm just going to go with the standard APA I-Joist. And you'll see here, and we actually added Canadian in there as well. So, but I'm going to go ahead with the standard APA I-Joist. It's just our generic I-Joist if you're not familiar with it. And I'm going to put these in horizontally at 2 foot on center. I'm going to say apply, and all I have to do is just click inside the bays. By clicking all around, you'll see I get I-Joist filled all across there. If you're ever wondering, hey, I don't really get to see what it looks like here, you can see the labels, but you also can turn on the shapes there so you can see what I was putting in. Sometimes just a lot of blue, you don't know what you've done. So it's sometimes helpful. You'll see there's a little button at the top to turn the labels on and the shape labels there for you. So next thing to do here before we move past that hallway is pretty blank. We need to put some, I'm just going to put some wood beams in place there, vertical instead. So I'm just going to change the direction of the framing. So let's turn that off now that it got a little crowded in there. And we can see I have wood beams across my hallway area, and I have all of my framing going in the horizontal direction for my I-joist. So I've got all that in place. I've got to put some diaphragm edge around my structure. So I'll go ahead and put a diaphragm. I have a choice between a rigid and a flexible diaphragm. I'm going to go with rigid diaphragm. And all I have to do is just say apply, and it will follow along the edge and automatically create that diaphragm for me. I'm going to create an opening inside of here. So I just push apply and click inside to create an opening. So now I have an opening in my frame, in my elevator bay. I've got all of my framing around my structure. One piece, let's look at our floor levels here. So we came in, we created a new floor. Let's actually call that first floor. We can name it whatever we want, but we've got an elevation of 30 feet. It's using residential, which is good, and it's going to be, but it's using a deck default of concrete. That would not be good. We want to change that to be wood. And the decks here, so decks are going to be for the beam supported floors. And you can go ahead and look at your deck definitions you have. We're right now using a 1-inch wood deck across the entire structure. It's got an unbraced length here of 1 foot. So every 1 foot, my beams are going to be supported there. And you've got max span of 4 feet, which is going to be like what your plywood kind of decking is, can go for a max span. If you got here wood, and you'll see the self weight. So really what's happening is that for when we're in the beam supported floor, all we're doing is just doing load attribution, applying that in the wood direction here. If we're applying it right now, in the direction is 0. So most of our structure is actually not in the 0 direction, 0 meaning horizontally across my screen. That wouldn't really work. So we're going to change this because most of our structure is going to be in the 90 degree. So it's in up and down on my screen. The only piece is that hallway. So if we look, I'm going to show the default for my deck. With the default, you'll see everything is going up and down. So that works everywhere except in this little bay in the middle for my hallway. So that's the only place I need to define a deck. And so the rest, it's going to be using the default, but I'm going to click on that deck, and I'm going to say go to use the wood deck horizontally. And so it tells me plan to the z-axis, parallel to the z-axis, which is horizontally on my screen. And I can say click within a box, an area, or box or deck area perimeter. So what I can do is just grab that edge and drag it across. And you'll see all of a sudden now it shows me that it's applied over the default deck. So the idea with default decks is to make it quick and easy for you. So most times if you have the same direction infill framing or whatever, you will not need to worry about your decks. And you only need to do the decks where you have different directions for your framing. So that's kind of an easy way for you to do that. So I've got all of my walls in place. I've got my deck in place. I've added my diaphragms. The last little piece here, I'm going to turn off those diaphragm edges here, say none. The last little piece, I'm just going to add some openings in a couple walls just so you can kind of see. I don't want to get too involved in openings, but it's really easy. All you just do is double click on a wall, and you'll see double click on that wall and click on the draw openings, and you can click. And now this is newer. In the lower right corner, you'll see that there's coordinates. And so you can try to find where you are in that wall. And once you start clicking, you'll see that those coordinates grow. So it helps you size that opening for yourself. So just a couple walls I'll do. I don't want to spend too much time on that, but you'd wanted to do obviously a real structure. You'd want to put openings in all of those walls for yourself. Okay, so I've got all of that in place. The last thing we can do before we move on here is let's go down to that lower floor and let's just take a look. I'm going to turn off this here. Let's take a look at what's going on this floor. We said we had a default area load on this structure here of retail. But when we don't have the structure sitting on top of it, so where you can see we can put the floor on top, that's actually going to be like our roof area. So that would be, we have retail inside of that area, but where the structure, maybe people can walk out onto that roof area. That can be multi-use. Lots of times in New York, we used to put gardens on that type of, on top of the podium, things like that. I saw something similar in Austin this weekend where you got to see like gardens up there. So in that case, you might put a ton of weight on that area. We're just going to call that a roof area. So I'm going to go ahead and draw in an area load. So draw area loads, and I'm going to choose here the roof area load, and choosing it to draw it by point to point. That allows me here to just click on an edge here. So I'm going to click around the structure, And I'm going to go all the way around here, and I'm going to grab a point, another point here, and clicking these points, I will be able to, you can see here now that's showing us all of the roof area load that I've just added. So the same thing I'm going to do over here, this little piece here, maybe this is just a balcony off of somebody's residence here. So you got a little piece of different, we're seeing different area loads on that. It's kind of easy to turn it on with default as well. So if you see there's retail, which is that blue color, and then roof is going to be that pink area. So I just kind of put that on those levels there for us to see. So we've got our loading in place for our slab level, our loading in place for our wood level. I'm going to turn off the underlaying so that show another floor so we don't have to see that. And let's just turn off the area loads there. Okay, so before I keep going, what I like to do is I always like to run the model just to see that everything went okay. So I'm going to add more floors to this, but it's just good practice to say before you get too deep into the model, a lot of times people just go to build a giant model and then things aren't working on the lowest levels. So in good practice, just to make sure, I just run the model and it will just carry the loads down the structure. It'll check what's going on in my wood structure. It'll check what's going on in my concrete floor level, so my slab floor, and it calculates everything. So especially in a small model like this, it's not going to take me more than a couple seconds here to go through each floor and just check that I did those things right. So we should see design in all of our wood. We should start to see some reinforcement design on the lower level. Obviously, it's not to the level we want yet because we're going to be adding 2 more floors above it, but it kind of helps us get it past that stuff. So looking at this floor level at the wood structure, we can see, got it. We've got some I-Joist design here, which is what we were looking for. So we can easily take a look, maybe at this point too, review it, say, does this make sense to me? If not, then maybe I forgot to change the direction of my deck and I'm not loading it properly. But you can click on a detail report. And then you can kind of start to see, okay, let's see, what did I expect for loading in here? I have some service loads and some live loads in there. I see what my shear and moment diagram is. I start to scroll below and find out what my bending and my shear and what's controlling this design, deflection. So you can kind of start to see all of that, what is happening in the structure. Maybe I start to say, I want to create more design rules so that I force some of these smaller I-joists to just match, just might help you. So then start to define some design rules. For walls and stuff in here, all you're really going to get at this point is gravity design. So RISAFloor is just counting up down the gravity, down the structure. So you might not really care too much about what happens in here just because it's just gravity, and we told the program to use 16 inches on center. So we probably are okay. Nothing's really going to be going wrong if we're just counting on one floor level. The floor below, we can see that we are going to be getting some design on our structure. So we're looking at the reinforcement design, but we don't care just yet because we do want to add those upper floors before we start to really worry about what's going on in there yet. So to add the upper floors, it's super easy. You just go to Insert, Floor, and say we want to break the solution, yes. And now we're going to be adding a beam supported floor. We're going to create a copy of the floor. Now you have a first floor and actually, I didn't rename that, but that should be like our garage or our retail level. We're going to jump and copy the first floor, which is what we're looking at right now. We can call this second floor while we're doing it. And we can say to the program, hey, we want to copy everything, the columns, the beams, the decks, the loads, and also the walls from below. So copy everything we find on there and put that at elevation 45. We're going to use the residential loading, and we're going to call this a wood deck with a default angle of 90 degrees. You can say okay, and it creates that for you. You go ahead and do it one more time. Everything is remembered. That's a very RISA aspect here. All the things you just did 2 seconds ago should be remembered. All you have to do is enter in some information that might be different. So we'll call this, we said that was second floor. This will be third floor. And say okay. Oop. Sorry, you have to change it to copy, not a concrete floor. That wasn't proper there. And then we can say, okay, there we go. And so let's see here. So now looking at our structure, just double check. Kind of a nice way to look at it is to look at it in the 3 dimensions. You can start to see here we've got our 3-dimensional model. It's going to be having 3 wood floors above. You can keep going. There's no stopper on that. Obviously, it's the material that's going to govern how high to make it. But we've got, I'm just kind of picking a 3 stories above there for our simplicity of our model. So I'll go ahead and run this again. I'm going to solve the model. It now is counting down all the loads from those floors above. So we're now going to take just a couple more seconds here beyond what we did prior. It's optimizing the shapes. It's going to be calculating all those gravity loads down the structure. So we might see a little bigger sizes. If we were looking at columns for walls, obviously we're still pretty much okay. But maybe the lower level of our structure might start to size up. We're now supporting a lot more at that lower level. So we go through, and there's a lot of optimization. Sometimes it takes just a second, but we can see we're now already on our first floor. It's calculating all of that design of that reinforcement on the lower floor for us. Here we go. I'm going to just ignore that. There we go. Okay, and let me jump to, so we can see, we still see the same type of information on this upper floors here. So we should be seeing identical, which we do. So all of the floors are identical. The lowest floor here, let's just check our concrete podium level. So I'm going to turn this off for a second. We are looking at, this turns actually into a submesh. So let's take a quick look at, if we look at our designs of this lower level on the slabs, we can see, we can check out any of our contours on this slab if we wanted to look at what would be here. We can just apply. We see all the contours in the shear and the moment. So it gives you a great idea of what's happening in there for your different forces through the structure. Obviously, it's a great way to understand a two-way slab because you see the two ways, forces traveling through it. The other thing you can do here is we can look at the outline of the plates. Internally, the program is submeshing this into plates. So you'll see that it's a mesh of different plates, and that's how the program is doing an FEA of that and calculating all the forces in each plate, and then we can see the contours from that. So not typical that you need to go this level here, but it is very nice to be able to see it. And so we can let's go ahead and get rid of those plates for a second. There we go. But what is important is to take a look at the results. So if we look at, we have each one of those plates has a point deflection. So you can go through point by point. That's kind of tedious and probably not very useful. But if you did need to get down to that level, you could. Each of one of the plates corners has a point, and this would be reported for you there. But what's more important is that you see the slab strip deflections. So each strip, I'm going to turn those strips back on, has a number. And we can see those strips, so SL2, SL3, we see those strips, and the second number is the span. So when we look at this, let's go back to just that so you can see it. SL3, span 1, that's the support line 3, and that's the first span. This would be the second span. That's support line 4, and that's the first span, and the second span is S2. So when we look at the results, we look at the slab strip deflections. We can see they're broken into the support line and span. Now, the deflection information is listed here. It tells us the actual deflection per the dead load and the live load, and then dead load plus live load, and then it gives us a ratio. Now, ahead of time, before we actually went into design, there is a slab definitions, but we also had slab design rules. And in here, you'll see that there's a deflection tab. Right now, for the north, south, and the east-west, we're telling the program what the ratio that is acceptable for dead load and live load, and then dead load plus live load. So you could put a maximum in inches there if you wanted to, so the deflection, what you'll allow. And whenever this is exceeded, you'll see in the results, it turns red. So I'm seeing lots of red numbers in here. We're exceeding the deflection. Oftentimes, you're going to be seeing deflection as a controlling number in a lot of different designs. So we see deflection as being exceeded. We also see, if we go to there, we can see our results for our rebar. So we've got rebar, and you see unity check. So this is the unity check. I don't see red in here. I don't think I see. Let's keep going down. So it looks like our unity check for our top and our bottom are working for our reinforcement. But still, we're not going to be working out well once we get to the design because we have too much problems with our deflection. You can also look at your punching shear, and that's another point of that usually has a problem. If you're having the slab issues, it would be your punching shear, and we've got really big numbers. They're all red, so those numbers are just not adequate. So what could you do? You could start thickening the slab in different areas, things like that. But I'm going to go ahead and just say, we've got too much bad deflection for the entire slab. So let's just bump it up to 14 inches. And we'll go ahead and do 14 inches over the entire slab and see if we can get past our deflection issues. So once we go to a thicker slab, hopefully that'll cure some of our deflection problems. And beyond that, we'll examine what we have problems if with reinforcement. Maybe reinforcement will go down because of that thickened slab for the whole thing. Sometimes you have to do a balance between thickening the slab versus thickening a portion of the slab. We're also going to talk about shear caps. So maybe the punching shear is still an issue. We can take a look at what to do there. So we rerun the entire solution because you don't just thicken the slab. You're changing force distribution throughout that whole slab. So the wood structure is sitting above it. It's going to be distributing it differently based on how it deflects, things like that. So go ahead and see. Now let's take a look at our slab strip deflections. And everything is working out okay. So we've got all of that working. I'm going to go ahead and look at the next piece is our punching shear. So punching shear is still an issue, but we don't see 2s anymore. We just see like a high of 1.7. The way we can investigate this further is let's look at the detail report. And you'll see that that was an interior. It shows us what's happening in this punching shear calc. It gives us an idea. It's showing the slab is failing. It's giving an L1, so that perimeter here is going to be 24 inches and 28 inches. This is actually a big column, 16 by 12. So what we can do is add some shear caps for this entire thing. You might say, hey, you can just thicken the entire slab, but maybe it's cheaper, depends on where you live. Is it cheaper for you to build a shear cap? Maybe that's more. If you want, you can do shear caps here. All you have to do is just add a shear cap. I'm going to say fill the whole block, add shear caps on every column. That's definitely a question you have to ask yourself, is that worth it? But let's just see, I can do a 48 by 48 shear cap of 6 inches extra. So it's not a lot, but it might get us past all those problems with those punching shear. Form work, things like that, whether that makes sense to you. Maybe you just bump it to a 14.5-inch slab. Maybe that would help you because we were pretty close on punching shear. And then maybe go 1 by 1 column, add shear caps where you need them explicitly as you increase the slab thickness. But a lot of these things too are design questions. You'd say, hey, does it make more sense to you as the contractor says to you, that's too much money for me to do one-offs. A lot of times in design practices, we tend to do just the same so that we won't worry about design issues where one column was thickened and one wasn't, having a shear cap. So capital, shear cap, all those things are terms for what we just added there, which is just a thickening of the slab. And internally, the program is actually thickening the slab in the FEA. So it really is going to distribute the forces differently. So if we look at that punching shear numbers now, we see that they are all working now. Okay, so we have no problems there. We can look at one of those now. Let's just take a look at one of these here detail reports. Once we've added that shear cap, you start to see, okay, it shows here it's adding an additional 6 inches, and that means that the slab check was less, and then we scroll down below, and now the shear cap is governing, but its unity check is only at 70.72, so we're fine on this now. So that kind of helps us work through all of the issues in the slab. For the design of the reinforcement, we can just take a quick look at that. So you see that the program is breaking it into column strips and mid strip left and mid strip right. So wherever you have a support line, that's going to be cutting in, making those actual support lines for you. So what we can see is if we go, let's see, we can see the reinforcement. So this is the bottom bars, and you'll notice here, so you zoom in, you see each area, the column strip and the mid strip left and right are being designed separately. So when they're common here, so this one's at 18, 8's at 18, it's going to go across there. This one here is at different spacing. This internal one here, this column strip needs a 17-inch. So you'll see it tries to fit them all the same if they can. If we can go to the top, let's go to the top bars. You'll start to see here, we're going to be in the top bars, number 5s. And you can control the slab design rules. That was where we saw the deflection, but the reinforcement here is just set right now to be number 5s on top and number 8s on the bottom. Maybe that doesn't make sense for you. Maybe you want to set that to be all number 6s, whatever you can do, and it will change the design for you. To look further into that design, I'm going to click on here, and you'll see that you can click on the detail report. And this detail report starts out with the total detail information. So shear and moment, what were the forces in that entire design strip? When I say the entire design strip, that's what I'm talking about, is this entire block, without worried about column strip, mid strip. It's just the entire forces across that entire design strip. When I want to drill down to what the reinforcement is, I would go to a column strip or a mid strip left or mid strip right. And inside of that, it gives me the reinforcement. So I see that what the reinforcement is required. So it's number 8's at 18. It gives me the inches there. Scroll below that, I see the forces it required. And then it starts to tell me what the governing cuts were. So the cuts are broken into by clicking on cut. This is our governing cut, and it tells me what this bottom reinforcement was controlled by this 4/3 rule here. That's in green. It's telling me that's what's happening in this one strip, what governed it. But you can click between all the different cuts. Internally, the program is making cuts across each of these design strips, finding the forces, designing the reinforcement, and then it envelopes that in order to find the maximum and minimums to find what you need for the entire span. So you can see as you scroll across, you'll get different reinforcement requirements, and the program's finding this worst case and reporting it back to you in that strip. But it gives you a good tool in order to find what happened in that reinforcement design. So you've got all the reinforcement design here for your entire slab placed in our slab results and rebar. So you'll see that shows you all that, top bars, bottom bars. You can export this right to a DXF so you can have it on a drawing for yourself, and you can go from there. Okay, once we've got all that in place, we have our whole gravity system in place. The next piece is to take it over to RISA 3D. So using the director button at the top right corner, go to RISA 3D. I'm going to actually grab a model here that I have, just has a little bit more of all my steps here. So I'm going to go ahead and say yes, and it has a solution present for us. And go ahead, let's close that. There we go. So using the director button, this is the same exact model here. I just added a few more openings for myself. And first thing it's going to ask you is going to be, what wind loads do you want to use? So the wind loads here, you have choices between where you're located, what wind requirements are. So ASE 710 is the latest and greatest. So I'll choose that. And I'm using 115 miles per hour. The base elevation can be based on where you want that wind to hit. So for example, if we had concrete level underground and not exposed to wind, we might put it at 15 feet. And then it will calculate that first level, being that first floor in wood, as our first floor that's exposed to wind. The program then calculates all the forces for you. So you can see the pressures listed here. You can see all the different forces. It breaks it in and calculates it based on the all buildings method. And we find a force in the X direction and a force in the Z direction. So you've got loads loaded directly into the diaphragm level. I'm going to say OK. And I see the similar type of input here for seismic. So you can put in the code you're selecting there. We have foreign codes as well. You can choose, I'll choose ASE 7. You put all your factors in for your structure. And then what you also do is here, you go and look at your location. So I grew up in New York, and this is actually my hometown location. So these are the seismic provisions for that. I put them in and calculate the loads for that. And I can see what the forces are. We calculate all of the different inputs based on the seismic provisions up here, and then we scroll down below that, and we see that it calculates the weight of the structure, and that weight of the structure, so you can see this is a great back of the envelope calc. So I always in practice, I take a look and say, okay, does this make sense for me? If I saw that the garage level was less than by far than the upper floors, that would be a red flag. But also just to make sure that I agree what that garage floor level is based on what the upper floor levels are, and then I can see the forces in the different directions. And then I see what the seismic force it's based on the seismic generation, what the structure looks like. So it will be doing eccentric loading, things like that. But this is my force right there. And then that's my total base shear. But this is the numbers you want to verify and make sure that you're in agreement with that. Say okay, and jump out of here. And all of a sudden you start to see, right as we pop out, you see that we have the diaphragm levels drawn right on top of our structure. So as I mentioned earlier, the only members that you wanted to come across to RISA 3D are the ones that we called lateral. So you'll note that there's no I-joists in here. Those are going to be left behind. But we do see the dead loads that we're contributing from those joists. They're on the walls that we need. So sometimes you get nervous, you look at it, you say, hey, I don't have all my structure. But the loads that were there are in place in the model so that you are getting accounting for their dead load, their live loads contribution is here. So you don't have to worry about that. But what you do get is you get all the loading from the lateral portion of a structure. So if we look at this and we look down on the structure, and I'm going to actually turn that there, this direction, you can see this is the wind loads in the X direction. We're applying a point load right into that rigid diaphragm. The lower level is a semi-rigid diaphragm. So it's going to be applied that directly into the semi-rigid diaphragm. And we can see that this is for the Z direction. We also do the same thing for the earthquake X direction. You'll see that a portion of the load goes directly into the diaphragm for the upper rigid diaphragms, and for the semi-rigid, it goes right into the slab, or what we then break into plate elements, and we'll be distributing it based on its stiffness. So we see all this for each one of our loads. So I'm going to actually go ahead and I'm going to open up. So I created some load combinations. I'm just going to solve those seismic combinations. You can create a variety of different loads here. I'm just going to, for speed for our model here, what we're going to do is we're just going to run a couple different seismic combinations and see how they apply into our model. So what we're doing, we're creating all of those loads directly. You'll see we're going to see the semi-rigid diaphragm, really helpful for us to see how that loads get distributed. And what you also know is that we are having all those wood walls just sit right on the diaphragm. Because it is semi-rigid diaphragm, it has some stiffness to it. We can let that just sit directly on top of the lower structure. So we've got a solution present. First kind of couple things I like to look at is to just look at our deflection. I'm going to turn off my nodes. And the deflection of the structure is important when you're looking at all these plate elements. Internally in a wall element, all the wall really is a plates. It's a submesh of plates. You can turn that on as well just to see. So if you look at your wall panels and show the mesh of those, you'll start to see that those are just broken into plates as well. So it's a really large plate model, but it's a lot automated for you so that you don't have to really worry about a lot of the stuff you would when you were doing your own plate model. So you'll see here, this is our semi-rigid diaphragm. I'm going to actually show this a little differently here. I'm going to turn off the top of the structure, and I'm just going to select the lower portion of my structure, and I'm going to look at this right here. I actually use the lock button, and then it allows me to turn off that upper structure for a second. So you can see I'm just showing the deflection on this lower level as we apply those loads. So I'm going to go ahead and show we're doing maybe load combination 15. So this is this load combination. As we apply that, you can start to see here, there's 14 and 15, what's happening in the structure. The other piece to find out in here, you can turn on our contours to understand in that slab. So in the diaphragm, we can look at how the forces are being distributed, maybe look at the moments. And we can see exactly what kind of the similar stuff we saw for gravity, but this is actually showing it as we apply some lateral loads. So if you ever needed to worry about designing that in any way, lots of times people for semi-rigid diaphragms don't really design it to take that force, that lateral force, but you can, as you see the moments and shears through the structure, if that is part of your lateral resisting system and you need it to take those. Otherwise, you can actually switch it to a rigid diaphragm as well to see that it's not actually, it's just fully rigid. As your slab gets thicker, those are decisions you start to make, whether you need to call it semi-rigid or when you want to call it actually a rigid diaphragm. Same things for your walls. You can start to play around and see how those walls get, let's see, contours on our walls, how they get distributed, how we're seeing there. So let me turn off my deflection just so that we can stop seeing that for a second. There we go. So you can play around with the contours on the walls and start to see how the forces are distributing inside of the walls based on the FXY. So that would be kind of your shear there. You can see that inside of each wall. This is our lower structure. If we look at the detail reports on any of our lower structure, this is going to be our concrete wall detail report, and it starts to tell you a little bit more information about what's happening, what the reinforcement requirements are. If we get reinforcement requirements here in RISA 3D that higher what then we had in RISAFloor, then we would carry that back to RISAFloor for you. So you'll always get the worst case design for your reinforcement, and you can see here that we get in-plane diagram. It starts to design all of that information for you for in-plane and out of plane. You can also see the masonry wall design as well. So masonry is being designed, calculating the in-plane and out-of-plane forces for you, and with a diagram for each envelope diagram there. On the upper structure, I'm going to unlock this upper structure and just show that for a second. So we'll go ahead and use that inverse tool, lock that upper structure. I'm displaying all right now the contours. Let me turn the contours off just so we can see a little bit closer what we're looking at. So for these walls here, for these wood walls, if we want to see the wall design results, an easy, quick way to see all of the wood wall design results and all of the concrete in one place is going to be the wall panel design spreadsheet. So you'll see concrete design all in one location, masonry design all in one location. And then when we go over to in plane or out of plane, you can get wood design all in one location, in plane and out of plane. So you'll see it all listed there for you directly in that. It'll give you if it requires hold downs. So in this program, in this model here, we're not actually going to do hold downs. We will give you the strap forces because the straps are going to be attached to each from wall to wall. And then if you need strap forces, we're not hold down would assume here that you're at the very base of the structure. But to find out more information of this wall, you can click on the detail report. And in that side of that detail report here, it will give us information similar to what we saw on the concrete and the masonry. It breaks down the results for you here. So we see this wall is one region. Okay, so I didn't add any openings to this wall, but it gives us a shear panel design. It gives us the unity check. It'll give us any strap forces if there are any. It tells us what was required in that structure. And then deflection. Deflection is an important piece on that. So we have the deflection results based on the FEA. So you see the finite element deflection, and then the deflection calculation based on just a hand calc method. So it's a little different, and then you can actually change the stiffness of the wall if you want to try to get closer. The hand calc method takes things into like nail slippage and different pieces that when you're looking at a finite element analysis, you're not seeing that same exact hand calc method. So you can adjust your stiffness right inside of the wall panel spreadsheet. If I go to my regions, you start to see a little further about what the shear panel is doing. The size, you'll see the axial and the shear and moment diagrams, the chord forces, what was required and what was the capacities. So this is what we're looking at right now is a segment design. It means that each segment is being designed separately. I've also got a different example here. So if we look at, for the example, I did a force transfer around openings on the upper wall here. So that helps us calculate the force around each opening. And so we'll see inside of the opening report. It gives us the forces. It breaks the wall into segments. Each different piece or transfers the force transferred at each little piece. So you see 1, 2, 3, breaking it all the way to 8, and inside of that, what the force is calculated across that, and then the analysis requirements for that. So this one's pretty low, but you'd see that force transfer around openings allows us to get some calculations based on what's happening at each calculation at each point around that opening. Then it calculates there, based on that force required, what we have supplied for the shear panel. So I scroll down below that. Similar information gives us the chord forces for each side of the wall, and then that panel is shown there with the chords and the stud requirements. If we look at the one that's perforated, this one, the second one here has got a perforated. I chose, so inside the wall panel, when you click on a wall panel, it gives you the choice segmented. You can choose between perforated, force transfer, or segmented. So I actually, for some of these, I chose them ahead of time here, and I gave myself this one's got a perforated. So in perforated, it allows us to just kind of break the wall up into, kind of get rid of this opening area and just shorten it. So we have an overall length of the wall kind of is shortened. So the full height is 20 foot, while this wall is actually 32 feet in length. It just sort of cuts out that middle section and calculates the resistance based on just the full height sections. That's our perforated method. And as I scroll below here, I start to see here the design details, giving us what all the requirements of just that area and what the forces were. So we see the total openings. This is actually a great hand calc method to do. It's easy, and you'll start to, and we actually we laid out all of this detail report just to really, really easily match what you do for a hand calc. And then you see below here, you got chords and studs, and that whatever is required here. You'll notice I'm doing zeros for the studs. That is, I need to run a dead load plus live load case, which by itself, which I didn't do for this example. But you've got that. You can run all of your different examples here. You've got all those load combinations. Mine took seconds. I just didn't want to waste your time. But you would be running all these different load combinations, wind load, live load, as well as the earthquake loads all together. And then you'd be finding inside of that you're finding all your wall panel design information directly to make sure that is the controlling case and which one you're going to be designing for. So you'll see the governing load combination is going to be right here. So you've got all of that. I've just unlocked the rest of the structure. There's a lot of information if you were doing any, we didn't actually bring any beams across because we were relying, for our lateral system, we were relying on all of our columns actually just to support the lower level, but otherwise really you're just doing all your wall system is really the only piece that we had for our lateral system. Our concrete columns, if we had any reason to size those up, so in the case that our seismic was going so large that it was actually controlling some of the column design, this would be sized up. We'd see a unity check max above 1, and we could resolve it, and it would set with the suggested design. Right now, the program's picking just whatever came across with RISAFloor design. So you've got all of that different pieces in here, and you can then take this back to RISAFloor. So going over to RISAFloor, you can go back in here. If we sized anything up, it would be coming back. But at this point, I would then maybe take my model, going File, Export. I could send it to DXF. Once I send it to DXF, I'll start to see reinforcement and then all of the the slab. I'll start to see all of my information on my walls. If I'm on my upper level here, so I can create all of these different drawings for construction drawings. The other thing you can do is you can export over to Autodesk Revit. So instead of using DXF, you can do a Revit model. If you do a Revit model, a lot of the information that's carried across would be intelligent information. So it's not going to just be a label. It will come across with what actually this is as a shape, what the end reactions are. So a lot more information goes across. It's a very smart model when you take it over to Revit structure.